This is part 4, and this is strictly going to be number 7 on the worksheet. This is a fairly long, complex problem, but it's not hard. There's just lots and lots of steps. So I'm going to try to walk you through this one step at a time. Okay. The coefficient of kinetic friction for a 10 kilogram crate on a ramp is 0.32. The ramp is inclined at 23 degrees. If the box is given an initial velocity of 4.2 meters per second up the ramp, how far up the incline will it go before stopping? Okay, so we just got a little bit of information here. Initial velocity is up the incline, and it is 4.2 meters per second. Okay, the ramp, the angle of incline, is 23 degrees. The coefficient of kinetic friction is 0.32. The mass of the block is 10 kilograms. The final velocity, says it stops, is equal to 0. And we're looking for a change in position. Okay? Well, v squared equals v naught squared plus 2ad. So if I know an acceleration, I can use that equation. Or x equals 1/2 at squared plus v naught t. So if I had a time, I could use that equation. I don't have time and I don't have acceleration, but I do know a mass, I know the kinetic frictional coefficient, I know an angle, which means I can find all the forces, and if I know the forces and the masses, then I can get the acceleration, which means I really need a picture of what's going on because it's a force problem. Okay, so here's my incline, here's my box, and the box is moving up the ramp. Okay, so the velocity is this way. As always, label my forces. Okay, gravity always pulls down, force due to gravity. The normal force is always perpendicular to the surface, so here's the normal force. And friction always opposes motion, so here's the kinetic frictional force. Okay, and what I want is I want the acceleration of the block up the incline. Okay, so that means Newton's second law is net force, and since I'm looking up the incline, I'm looking in x, equals mass times acceleration. Okay, be careful. Kinetic friction is not the only force acting on this block, right? Gravity's got components, and so there's Fg in the x direction and Fg in the y direction. Okay, now this angle up here and this angle right here, they match. Alright, so net force in x is mass times acceleration, but net force means I got to add all those forces together. So I'm going to go ahead and I'm going to say down the incline is positive, at least for this part of it. And so these two forces, Fk and Fgx, act in the same direction. And so I have Fk plus Fgx equals ma. Alright, well, do I know Fk? I do not. What I know is the coefficient of kinetic friction, but I can use that to get Fk because I know Fk equals the coefficient of kinetic friction times the normal force. Okay. Do I know Fgx? Well, kind of. I know it's this component over here of the triangle. Okay, and I do know Fg. I know Fg is 10 times 9.8 mass times the acceleration due to gravity. Okay, so that's just 98. So what I have to do now is find all these forces so that I can get the acceleration. Fn. Okay, what is Fn? Well, in the y direction, the force is exactly balanced because it doesn't accelerate off the incline or into the incline, it accelerates down the incline. So net force in y is equal to Fn minus mg in y, which equals 0, no acceleration, so the normal force is equal to mgy. Well, what is mgy? It's the adjacent side to this angle, and so that means I got to use cosine, and so this is equal to mg cosine of the angle. Okay, so I'm going to go ahead, I'm going to put a box around that for now. We're going to need that information. Normal force is mg cosine of the angle. In fact, not only am I going to put a box around it, I'm going to go ahead and I'm going to use it right here. The kinetic frictional force is the coefficient of kinetic friction, so mu k times the normal force, mg cosine theta, plus FGX. Well, what's FGX? Well, it's the side opposite this angle. So FGX is mg sine theta, which equals ma. Now you'll notice there's a mass on this one, there's a mass on this one, and there's a mass on this term as well. So the mass actually drops out. However, I'm going to go ahead and I'm going to leave it in there for now just because it might come in handy later. I'm not saying that it will, but it might. Okay. Well, actually, if the mass cancels here, maybe it cancels everywhere. So let's go ahead. Let's take it out. Mass cancels, mass cancels, mass cancels. And so I'm left with the coefficient of kinetic friction, which is 0.32, times the acceleration due to gravity, which is 9.8, times the cosine of 23 degrees, okay, plus 9.8 times the sine of 23 equals A. Okay. Well, this is 2.887, and this is 3.83, which gives us a total of 6.72 meters per second. Now, this is not the answer to the problem. Okay, this is the answer to what the acceleration is. So the problem wanted to know the change in position. I just found the acceleration. The acceleration is 6.72. But because I know the acceleration now down the incline, I can find how far the box goes, because I know an initial velocity, I know a final velocity, I know an acceleration, I can get a change in position. Third kinematic equation. So final velocity squared equals initial velocity squared plus 2 times the acceleration times the change in position. And so 0 equals 4.2 squared plus 2 times, okay, now I got to be a little bit careful. Negative signs, right? It's moving up the incline, my acceleration is down the incline, so if this one's positive, the other one has to be negative. So plus 2 times negative 6.72 times the change in position, which is what I really want. Okay, if you do the algebra here and solve for that, you should get a change in position of about 1.32 or 1.31 meters. Okay, so this thing goes 1.31 meters up the incline before stopping. Okay. It says if the box does not stay at the top of the ramp, what is the maximum value for the coefficient of static friction? Okay. So again, we're dealing with this inclined box. Now it's up here at the very top. It moved its 1.31 meters up, and it's going to slide back down the ramp. Now it actually stopped for a brief instant in time right up here when it's no longer moving up the incline, but it hasn't started to move back down the incline. And that means there's actually static friction right there. Okay? And so if I look at my forces here, I still have the force due to gravity, and I still have the normal force, but I no longer have that kinetic frictional force pulling down the incline. Instead, I have a static frictional force pulling up the incline, right? Gravity's trying to pull it down the ramp. That means static friction is opposing it, pulling up the ramp. And I'm supposed to find the maximum value for the coefficient of static friction, assuming that it actually comes back down the ramp. Okay, well, if it's going to come back down the ramp, that means the x component here, FGX, has to be greater than Fs. So I'm going to go ahead and write that. FGX has to be greater than Fs. Otherwise, static friction wins and it stays at the top. Well, we know what FGX is. We calculated it up here. It's FGX is mg times the sine of the angle, mg sine theta. Okay, this has to be greater than the static frictional force. Well, the static frictional force is the normal force times the coefficient of static friction. But we know what the normal force is. We calculated it up above. So this is the static frictional coefficient times mg cosine theta. Okay? And I want to know the angle, which means I need to get the angles by themselves. Okay, so I'm going to divide both sides by mg cosine theta. Mg cosine theta, mg cosine theta. And so what I'm left with is, well, mass times gravity cancels, and so I get the sine of theta divided by the cosine of theta has to be greater than the coefficient of static friction. Well, this means that sine divided by cosine is merely tangent, so this is the tangent of the angle is greater than the coefficient of static friction. So if we take the tangent of our angle, which is 23 degrees, we end up with 0.424. So the tangent of 23 equals 0.424, which is greater than the coefficient of static friction. Okay, so we know our coefficient of static friction cannot exceed 0.424. If it does, then the static frictional force is bigger than the gravity in the x direction, and the block will stick at the top of the ramp instead of slide back down. Okay, C says, how long does it take for the box to come back down the ramp? Now, it's tempting to try to use all the same information that you have already, but you have to pay attention to what's going on, right? The block is at the top of the ramp. It's going to slide back down the ramp. Okay, so I've got the force due to gravity pulling down. I've got the normal force pushing perpendicular to the ramp, and then I've got kinetic friction, which is pulling up the incline. It's not down the incline this time, it's up the incline this time. Okay, but other than that, not a lot's changed. So we still have our components of gravity. It's just this time, okay, we're looking for a time. Okay, we know its initial velocity is 0 because it starts at rest at the top of the incline. And we know actually it's got to come back down the ramp. We know its change in position. It went 1.31 meters up the ramp. It's got to come 1.31 meters back down the ramp. Okay. What we don't know is an acceleration, and we're supposed to find a time. We don't know a final velocity, and we're supposed to find a time. So we need an acceleration. And that, of course, means we got to deal with these forces. So it's Newton's second law again. Net force equals mass times acceleration. And we're looking down the incline, so this is net force in x. Okay, well, the net force in x is mgx minus the kinetic frictional force, and this is equal to ma. Now, I want you to look very carefully at this. Okay, on part C, we said that mgx minus fk is the net force. How is that different than part A? Well, in part A, we had mgx plus fk, right? These were in the same direction. Now they're in opposite directions. There's no reason to do all the math again. If we know mgx and we know fk, we can just sub them in from above. It's just instead of adding them, this time we're subtracting them. Okay, and so fgx, I know right here, this is going to be 3.83. fk, I know this is going to be 2.887 minus 2.887 equals ma. And in fact, I've got to be careful because this was after all the masses were canceled out. So this just equals a. And so when I do this subtraction, I get 0.94 meters per second per second. Okay, this is the acceleration of the block down the incline. Now I want you to look at that. Up the incline, it accelerated at 6.72 meters per second per second. Down the incline, it accelerates at 0.94 meters per second per second. Okay, why is it so much faster up the incline? Well, because the two forces act together. Down the incline, the two forces act against each other. So the acceleration down the ramp is the 0.94 meters per second per second. Now that's not the answer to my question, that's just the acceleration. I'm looking for a time, okay? And so the acceleration I'm going to rewrite over here is 0.94. And so if I want a time, let's see, I know an initial velocity, I know a change in position, I know an acceleration. Second kinematic equation says change in position equals 1/2 at squared plus v naught t. Of course, the initial velocity is 0, so I don't have to worry about that. 1/2 at squared equals delta x, so I have 1.31 equals 1/2 0.94 times t. And if I do the division and get t, t is 1.67 seconds. Okay. The last part of this problem is actually pretty easy. How fast will the block be going when it reaches the bottom of the incline? I know the acceleration is 0.94. I just calculated the time it takes is 1.67 seconds. So v equals v naught plus at. Initial velocity is 0, so this is just acceleration times time. 0.94 times 1.67 equals 1.57 seconds, or meters per second. Okay, so you'll notice it's actually going much, much slower on the way down than it was on the way up, and that's because friction sucked away a lot of the energy. Friction acted against us in both directions.